Welcome back. A recap of what we did last time. I introduced the concept of stochastic processes as a collection, a sequence of random variables, and these random variables would be indexed usually with reference to time. We can have the index set as a discrete set or a continuous set depending on the application envisaged, and similarly the codomain of the random variable can either be a discrete set or a continuous set. We have different nomenclatures for the relevant type of random variables, discrete time discrete time stochastic process, and continuous time stochastic process, and so on. And then I talked about certain equations that govern the behavior of stochastic processes. I talked about the Chapman-Kolmogorov equation, the Fokker-Planck equation, and the master equation. We discussed all of that in the last lecture. Now we move on to the concept of Brownian motion, which in a sense is an application of the concept of stochastic processes. Let us start with the fundamental building block of Brownian motion, which is a one step unbiased random walk. One step unbiased random walk. What is a random walk? Let us discuss with an example. Suppose you program your computer in such a way that it picks out an integer randomly, and depending on whether that choice happens to be an odd integer or an even integer. If it is an even integer, say it moves one step upwards, and if it is an odd integer, it moves one step downwards. I repeat, you conduct a random experiment. Let us say, let us make it even simpler. Let us say you conduct a coin toss experiment. You conduct a coin toss experiment. If you get ahead, you move one step upwards, or the pointer moves one step upwards, and if you get a tail, the pointer moves one step downwards. The probability of getting a head or a tail is equal. That is why we use the word unbiased. So we have a single step, that is, you start at t equal to 0. Nothing happens up to a certain point in time. Let us say we call it a capital T. So, 0 to capital T is one time step. As soon as the time reaches capital T, you make the toss, and immediately the system reacts by moving one step upwards or moving one step downwards. This is the example of a one step random walk. Let me show it by a diagram. So, here is the diagram. You are at the origin of the coordinate system. As soon as the clock strikes t, which is the length of one time step, it need not necessarily be 1 second or 1 hour, it can be 1 unit of time, howsoever you define that unit of time. Not necessarily it has to be coincident with the conventional unit of time, it can be chosen as per the desired application. So, 0 to capital T, at point T the experiment is done, the coin is tossed. If it ends up with a head, the a particle or the pointer or whatever moves up one step, and if it turns out to be a tail, the pointer moves one step downwards. So, that means what? That means that t equal to capital T, we can have two possible positions of the random walker. Either he can be at the coordinate t comma plus 1, depending on whether the coin gets a head, or he can be at the point t minus 1, depending on whether he gets a tail. Clearly, from the symmetry, it is quite obvious that the mean of this random variable is 0. In fact, let us make it a bit more formal. Let us define a random variable x. Let us call it x1. Let us define this random variable x1. This random variable x1 can take the value plus 1 or minus 1 with equal probability. Random variable, I repeat, random variable x1 is can take the values plus 1 or minus 1 with equal probability. Therefore, the two values or the possible values that the system can take at t equal to capital T after the first step can be either +1 or -1, which is written usually in the form W1 of capital T. W1 represents the possible values of the system of the random walker at time t, and this can be represented by that the variable that we chose, that is x1, it can take the value +1, it can take the value -1, right, but the probabilities are equal. Clearly, the expectation of W1 is equal to the expectation of x1, that is 1 by 2 into +1 plus 1 by 2 into -1, that gives you 0. And if you work out the expectation of x1 squared, what do we get? We get the expectation of x1 squared is equal to 1 by 2 into +1 squared plus 1 by 2 into -1 squared, that turns out to be 1. So, the variance turns out to be 1. So, what are the critical parameters? The critical parameters are of W1 t. W1 t is the spectrum of values, the various possible values that the system can take at time t, and 1 represents the number of steps, which in this case is 1. So, W1, 1 represents number of steps, t represents the point in time, and that is equal to the expectation of this is equal to 0, and the expectation of W1 square is equal to 1. Now, we extend this to a two-step model. How do we do it? Let us look at the diagram first before coming to the parameters. Now, what we do is we split the interval 0 to t. Remember, we had an interval of 0 to t, and in the previous case we made the system made a jump at t equal to capital T. Now, the system makes two jumps within this interval 0 to capital T, but these two jumps are equally spaced in time. So, it makes a jump at t equal to capital T by 2 of +1 unit or -1 unit. In other words, the coin is tossed at t equal to t by 2, and whether it, depending on whether you get a head or a tail, the system jumps to +1 or the system jumps to -1. So, the possible positions at t equal to capital T by 2 for the system to be is +1 or -1. Thereafter, when the clock strikes capital T, the system again tosses a coin, or you toss a coin, and depending on whether you get a head or tail from its previous position, whatever that previous position was, whether it was +1 or -1, it makes a jump, a second jump, either to +1 unit from where it was or -1 unit from where it was. Clearly, from the diagram you can see that the possible values that the system can have at t equal to capital T after two jumps, the first jump at t equal to capital T by 2 and the second jump at t equal to capital 2, the spectrum of values that the system can possibly have are 2, 0 and -2, depending on where the system was at t equal to t by 2 when it made the second jump. It can also be written in this form W2. Now, 2 means there are two jumps, there are the number of jumps are equal to 2, and capital T means we are investigating the spectrum of values at time t equal to capital T. So, W2 capital T is equal to x1 plus x2. Remember, x1 and x2 are defined similarly. They are binary variables which can take the value +1 and -1, each with probability 1 by 2, but they are mutually independent. This is very important. How the system evolves in the second step is independent of how the system had evolved in the first step. In other words, that the result of the second coin toss experiment does not in any way depend on the result of the first coin toss experiment. So, we have E W2t is equal to E of x1 plus x2, x1 representing the first jump and x2 representing the second jump. Because the expectation of both x1 and x2 is 0, the expectation of x1 plus x2 also becomes 0. So, expectation of W2t is equal to 0. Let us look at the expectation of W2t squared. This is equal to E of x1 plus x2 square, which gives us E of x1 square plus E of x2 square plus 2E x1 x2. Now, because the x1 and x2 are independent events, I can write this E x1 x2 as E of x1 E of x2, because x1 and x2 are independent events, because the two coin toss experiments are independent, and we know that E of x1 is 0, E of x2 is also 0. So, this cross term x1 x2 term vanishes, and we also know that E of x1 is equal to E of x1 square is equal to 1 and E of x2 square is equal to 1. So, what we end up with is that E of W2 squared is equal to 2, and the variance of the possible values that the system can take at time t equal to t, capital T, if it makes two jumps at equidistant points in time 0 t by 2 and t is equal to 2. Continuing in this manner, you can arrive at the recursive relation which is given in the blue box here, W n of capital T, where n is now the number of steps, n is the number of steps. We have explicitly discussed the case of one step, we have discussed the case of two steps, now we generalized it to n steps. So, W n t is equal to where the system was at the n minus 1th step, and then it makes a jump either upwards by 1 unit or downwards by 1 unit in the nth step, and that is represented by x n. In other words, we get the recursive relation W n t is equal to W n minus 1 into t upon n, because each step is now of length t upon n, plus each time step is of length t upon n, and of course, in terms of variable it is plus 1 minus 1 always. So, it becomes plus whatever jump it makes in the nth step, which is x n, which is represented by x n, where x n is again, I repeat, a random variable, binary random variable which takes the values plus 1 and minus 1 with equal probabilities. So, now you can continue this iteratively and you get this expression which is shown in the second box. In other words, W n t can be represented as a sum of binary random variables which can take values 0 and 1 with equal probability, and most importantly which are mutually independent. X1, x2, xn all are mutually independent, they do not have any correlation between themselves, and W n t, the spectrum of possible values that you get at time t if the system evolves n times during 0 and t is given by the summation of x n, the summation being made over the number of steps. Now, let us look at what we get for the expectation values. The expectation value of W n t clearly is 0, because the expectation, if you take expectation of a sum is the sum of the expectations and each of the expectation vanishes. So, it is clearly 0, and similarly when we work out the expectation of W n t squared, slightly more care is required, but we again note that the cross terms would again vanish, because the expectation, again for the relation that I mentioned in the previous slide, E x y is equal to E x e y, and each of these two is 0. So, the cross terms will all vanish and we will have expectation of summation of x I square is equal to expectation of x I square summed over 1 to n. Each of these is 1, each of these expressions is 1, this is 1, and therefore, because you have n ones, so the total becomes n. In other words, for an n step random walk, the expectation and variance of the spectrum of values at the end of the walk at time capital T is given by the expectation as 0 and the variance as n, where n is the number of steps. Now, this is very important, the n is the number of steps. Now, let us look at the situation more carefully, more analytically. What we want at the end of the day is a framework, is a design that enables us to do continuous operations, mathematical operations that involves continuity and differentiation. Now, in an effort to move towards that from this discrete framework, this is so far what we have done is a totally discrete framework. In order to move from here towards a continuous framework, the obvious approach is to reduce the length of the time step, in other words to increase the number of time steps between 0 and capital T. As you increase the number of time steps, you move from discrete time to continuous time, right. So, let us see what happens when we move from discrete time to continuous time. Now, recall that for an n step binomial tree over time t, capital T, the mean is given by 0 and the variance is given by n. Now, as n tends to infinity, in other words, how do we implement this program of moving from discreteness to continuity? We implement it by taking n tending to infinity limit. So, as you move from n tending to infinity, the number of steps increases. What happens to the variance? Clearly, the variance also increases. Greater the number of steps, greater the variance, and as you approach infinity, the variance also becomes unbounded. The process diverges. Now, because the process diverges, it becomes incompatible to a number of applications in physics and finance, and therefore, we have to evolve a mechanism whereby we can curtail this blow up of variance to a convergent situation where the variance converges to a certain number, so that the applications can be the spectrum of applications can be increased, particularly in physics and finance. Now, how can we do that? Clearly, the variance as we go from the discrete framework to the continuous framework, the variance goes up with the number of steps. So, if we scale down the time, instead of or if we scale x, the jump in terms of x under root x upon under root n or x into under root 1 upon n, then what happens? Then if you work out the entire thing again, the variance now turns out to be 1. The variance has now become finite, the variance has now become convergent, and by decreasing the step size, or rescaling the step size in such a way that instead of having a step size of plus minus 1, now I have a step size of plus minus 1 upon root n, then I find that the variance converges to 1. But then again we have a problem, because the variance simply remains 1 irrespective of the number of steps or irrespective of the dynamics of the system. How the system involves is does not impute itself or does not imprint itself on the variance, and therefore, we have to look for something better. Very often we find that in applications or in some of the applications, the variance tends to increase with time, it tends to increase linearly with time. To incorporate that, we make a slight modification to our program of rescaling. Instead of rescaling x to x into under root 1 upon n, instead of this rescaling, I introduce a factor of t here. How do I do it? I do scaling in this form. I move from x to y and write y as under root t upon n. What does it mean? It means that the jump size, instead of being plus minus 1, is now plus minus under root t upon n. I repeat, instead of the jump size being plus minus 1 which we started with, we now are looking at a jump size of plus minus under root t upon n. Remember, the time step continues to remain at t upon n. So, a quick summary of what we have at the moment: W n 0 is equal to 0, that means the system starts or the particle starts at the origin. Number 2, the number of steps is n, the time horizon is t. So, the length of each step is t upon n. Up and down jumps are now rescaled, instead of plus minus 1 to under root t upon n plus t upon n and minus t upon n. The probabilities remain unchanged. The probability of the up jump and the probability of the down jump remain 1 by 2, and to that extent we are continuing with the system being unbiased. Let us now look at this. So, what do we have? The W and T can now be described by summation of W and T can be described by summation up to n of I y I, where y I is given by under root t upon n x I. X I was binary, we are taking values plus minus 1 with probabilities 1 by 2 each. Therefore, y I takes the values plus under root t by n and minus under root t by n with respective probabilities 1 by 2. And the recursive relation now gets modified slightly. Instead of W and T, instead of x and t being here, we now have y and t. Otherwise, it is more or less the same. The substitution is, instead of, because the step size has changed, the step size have changed. So, when the object moves over the last step, when it moves over the last step, its jump is going to be either plus root t by n or minus root t by n, instead of it being plus 1 or minus 1. This is reflected in this term y n. Right. So, the critical parameters, the mean value will continue to be 0, no problem with that. The variance now will become, recall that the variance earlier, when the size of the jump was n, now the variance, if the entire process is relooked into, the variance will become, because you see you have rescaled the variable by a factor of t by n. So, the under root t by n, I am sorry. So, the variance will get rescaled by t by n. So, earlier the variance was n, now the variance will become n into t by n, and that is equal to t. That is the time horizon of the evolution of the process. Just to repeat, since you have rescaled each random variable that comprise the entire stochastic process by under root t by n, the variance also gets scaled not by this factor, but the square of this factor, that is t upon n. Earlier the variance was n, so it now becomes t upon n into n, and that becomes t, that is the length of evolution of the system. Please note, we have not taken any limits tending to infinity so far, which we will do right now. But before we do that, this was for the complete evolution of the system. What about an arbitrary time during the evolution of the system? Let us say this is my system, this is my 0, this is capital T, here is some arbitrary point small t. What will be the number of steps between 0 and small t? They will naturally be n into t upon capital T. Why is that? Well, the length of each step is capital T upon n. Now, this distance is small t. So, the number of steps will be small t divided by capital T upon n, that comes to n into small t divided by capital T. And therefore, when we work out the mean, obviously it tends to remain 0, and the variance now becomes summation of y, and the number of variables involved will be n small t upon capital T, and therefore, when we do the simplification, it will be, the variance will be n t upon capital T into t upon n, that is equal to small t. This is the variance of Wn of small t. Again it is equal to the length of evolution, it is equal to this length. The variance is equal to small t. These two things are important. A mean is 0, the variance is equal to small t, where now t is any arbitrary point. Please note this, t is an arbitrary point, t is not the total length of evolution of the system, t is simply an arbitrary point. So, that is important. Now, we move to the next step. As far as WNT I have explained, I have reiterated also, WNT is the spectrum of values of the process, the possible values that the process can take at time t. These are realizations of the random walk. The first case is when there are 16 steps, the second of 64 steps. You can see the zigzagging increasing, and the third is 256 steps, and the fourth is 1024 steps. You can see the amount of zigzagging in the fourth step. Now, what happens? So, when we take the limit, we arrive at a certain mathematical structure. This mathematical structure has a very significant role in the entire gamut of stochastic calculus. It is known as Brownian motion, and we now arrive at, or we now derive the expression for the, or the salient feature or the defining property of Brownian motion, and then we talk about its various properties. So, remember, so far we have not taken any limits, and we can move from this to the limiting structure to the continuous framework using any of these three approximations. We can use the central limit theorem, we can use the diffusion PDE, or we can move with the Stirling approximation. I have already given an introduction to the Stirling approximation when we talked about the Gaussian distribution as being a limiting case of binomial distribution. So, that gives you a feel of how that this particular case could be manipulated to arrive at the continuous limit. I shall start with the central limit theorem, and then I will also discuss the diffusion partial differential equation. So, this is where we stood at the last slide. We had defined the random walk, and we had defined the random walk with the property, with three fundamental properties. The length of each step is capital T upon n time step. The jump is equal to plus minus under root t upon n, and the probabilities of the jump are 1 by 2, and the system starts at the origin. These were the four fundamental properties that we had just till now. We had not taken any limits so far. Now, what happens when we take the limits? Remember, what does the central limit theorem say? The central limit theorem says that if I define a variable, suppose we have a set of variables x1, x2, x3, xn, all of them are IIDs, that is independent identically distributed variables with a mean of mu and a variance of sigma square. Then I define this variable sigma xi, summation of all these variables x1, x2, x3, xn, minus n of mu, mu is the mean. So, n into mu, and divide the whole thing by under root n sigma square, under root n sigma square, and this expression will be a standard normal variate in the limit variable, standard normal variable in the limit that n tends to infinity. This is what we will invoke in moving from the discrete framework that we have with us to the continuous framework. Recall, in our case mu was equal to E of yi, which was 0, and as far as E of yi square was concerned, it was equal to t upon n, because we multiply yi was nothing but, just to recap, yi was nothing but under root t upon n xi. Now, the stochastic part is xi, under root t upon x is not stochastic. So, when you take the expectation of both sides and square this, this under root t upon n can be taken outside the expectation operator. You get t upon n e of x I square. E of x I square we have already discussed, it is 1. So, e of y I square is equal to t upon n. Therefore, the variance of y I square is also t upon n, and this holds for each and every y because they are identically distributed. Hence, by the central limit theorem, what do we get? Summation of y I minus mean is in our case is 0, and under root n t upon t, because the number of steps is n t upon t. Recall that we are talking about an arbitrary length in the Brownian motion evolution, or in the evolution of the random walk. Arbitrary length corresponds to the number of steps being n t upon capital T, and therefore, instead of n we are using n t upon capital T, and we are simply now going to substitute the values. So, this expression is 0, the mean is 0, and sigma square is equal to capital T upon n. So, when you put capital T upon n here, we are left with under root t, n cancels with this n, t cancels with this t, we are left with simply under root t in the denominator. So, this whole thing simplifies to summation n t upon capital T tending to infinity, sigma of y I upon root t, and this is normally distributed as a standard normal variable. And therefore, we find that summation of y I, which is nothing but w n t, is not in the limit that n tending to infinity, number of steps moving to infinity, or n t upon capital T tending to infinity, if you are talking about the final of a particular arbitrary length, then in that limit summation of y I or summation w of t is equal to tends to the normal distribution with a mean of 0 and a variance of small t, which is the arbitrary point time length at which you are working out this analysis. And obviously, if you work out the analysis or you work out these parameters over the entire evolution of the system, then this becomes n of 0 capital T. So, just a quick recap, we have the mean of we introduce the variables y I here, y I is equal to under root t upon n x I. Therefore, because the mean of x I is 0, the mean of x I square is 1, we simply get mean of y I is equal to 0, mean of y I square is equal to t by n, and therefore, variance of y I square is equal to t by n. Substitute in the expression for the central limit theorem, we get summation of y I upon root t is equal is distributed as a standard normal variate, and therefore, but summation of y I is nothing but the w n or w infinity, or at the moment when you are taking the limit w infinity of t, and that is normally distributed as 0 t, because summation y I is distributed as summation y I upon root t is distributed as n 0 1. Therefore, summation y I is distributed as n 0 t, and summation y I is nothing but w n or w infinity of t, and that is what, in other words, what have we concluded? What have we concluded? We have concluded that the spectrum of values at any arbitrary point in a process that follows Brownian motion is normally distributed with a mean of 0 and a variance equal to the time since its initiation, or time since the origin of the Brownian motion to the point at which it is being assessed. We will continue after the break. Thank you.